You've never touched anything in your entire life, not once. Sounds ridiculous, doesn't it? You're holding something right now. Maybe a phone, maybe a cup. You feel the weight, the texture, the temperature. How could you have never touched anything? But this is exactly what Feynman loved to do. Take something you're absolutely certain about and show you that your certainty is just a comfortable illusion your brain built so you don't go insane. Think about the table in front of you. Solid, firm. You can knock on it and hear the sound. You can rest your weight on it. But that solidity is a lie. The table is made of atoms, right? And atoms, if you really look at them, not with your eyes, but with mathematics, with experiments, with naked reality. Atoms are almost completely empty. Almost completely empty. Let that sink in for a second. If you took an atom and scaled it up to the size of a football stadium, the nucleus would be a pea at the center of the field. The electrons, tiny particles orbiting. No, wait. They don't even orbit properly. But we'll get to that. The point is, between the nucleus and the electrons, there's an immense void, a gigantic nothing, and that's what makes up you, the table, everything. So why the hell don't you fall through your chair when you sit down? Why doesn't the table collapse when you rest your arm on it? Here's where the real mystery begins. The answer isn't because atoms are solid. They're not. The answer lies in something far stranger, something your intuition can't even process correctly. It's electromagnetic repulsion. The electrons in your hand are being violently repelled by the electrons in the table. You never touch the table. You float above it, separated by microscopic distances, kept away by invisible forces. Every tactile sensation you've ever had in your life is an illusion. It's repulsion. It's force. But it's not touch. And this is just the beginning. Because when you start really looking at atoms, when you start asking simple questions like, where exactly is the electron? Or what size is it? The answers don't make sense. They don't make sense in such a profound way that physicists in the early 20th century literally fell into depression trying to understand. Feynman used to say that nobody really understands quantum mechanics. Nobody. Not even him. And he won a Nobel Prize working with it. But the difference between Feynman and you is that he accepted that nature is strange. Not strange in the sense of, that's curious, but strange in the sense of, this defies all human logic and yet it's true. Let's go slow. Back to the atom. You learned in school that electrons orbit the nucleus like planets around the sun, right? Forget that. That picture is wrong. Completely wrong. It's not that it's simplified. It's fundamentally mistaken about what an electron is. An electron isn't a little ball. It's not a thing that's in a place. When you're not looking at it, and by looking I mean measuring it somehow, it's not anywhere. It's everywhere at once. It's a cloud of probability. A wave spread throughout space. Can you visualize that? No. Your brain wasn't made for this, but it's real. And when you finally measure where the electron is, when you finally interact with it, then it decides to be in one place. But before that, it was literally in multiple places simultaneously. It's not that you don't know where it is, it's that it isn't anywhere specific. This sounds like cheap philosophy, like quantum coach talk selling manifestation courses. But it's not. This is what experiments show, repeatedly, without room for doubt. The weirdness gets worse, much worse. Imagine you're throwing tennis balls at a wall with 2 slits in it. Behind the wall, you have a detector that shows where the balls land. What do you expect to see? 2 strips, right? 1 behind each slit. Some balls go through the left slit, some through the right. Simple, logical, the way the universe should work. Now do the same thing with electrons. Tiny particles. They should behave the same way, shouldn't they? They're particles. They have mass. They have charge. Fire them one at a time through 2 slits and watch where they land. But they don't make 2 strips. They make an interference pattern. Multiple bands of hits separated by empty zones. The exact pattern you'd get if you sent waves through the slits, like ripples in water interfering with each other. Waves do this, particles don't. So maybe electrons are waves? Problem solved? No. Because here's what breaks your brain. When you fire electrons one at a time, literally one single electron, wait for it to hit, then fire another, you still get the interference pattern. Eventually, after enough electrons hit, the pattern emerges. 1. Electron at a time. How does one electron interfere with itself? How does it know there are two slits if it only goes through one? Or does it go through both? Yes, it goes through both, somehow, simultaneously. The single electron exists as a wave of probability that passes through both slits, interferes with itself, and then collapses into a single point when it hits the detector. But wait, what if you get clever? What if you put a detector at the slits themselves to see which one the electron actually goes through? Then you'll catch it. You'll know the truth. You do this. You set up detectors. You fire the electron. The interference pattern disappears. Just by watching, just by measuring which slit the electron goes through, you destroy the wave behavior. Now you get two strips, like normal particles. The act of observation changes reality. This isn't philosophy. This is measurement. This is data. Feynman called this the only mystery of quantum mechanics. Everything else, he said, is just this same mystery dressed up in different clothes. You're not misunderstanding this. It really is this insane. The electron behaves like a wave when you're not watching, and like a particle when you are. And nobody knows why. Not Feynman, not Einstein, not anyone alive today. Einstein hated this, absolutely hated it. He spent the last decades of his life trying to prove it wrong. He couldn't. The universe, it turns out, doesn't care what Einstein thinks should be possible. Bohr, another giant of physics, told Einstein to stop complaining. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. What we can say, not what is, because maybe there is no is until we look. This should disturb you. It disturbed everyone. Schrödinger created his famous cat thought experiment specifically to show how ridiculous this interpretation was. A cat in a box, both alive and dead until you open it? Absurd. Except the math works. The predictions are perfect. To this day, no experiment has ever contradicted quantum mechanics. Not one. Here's another thing that shouldn't be possible. Atoms exist. Think about it. You have a nucleus, packed with protons, all positively charged. Positive charges repel each other, violently. Put two protons close together and they should fly apart. The electromagnetic force should rip them to pieces. So why doesn't the nucleus explode? There's another force, the strong nuclear force. It's stronger than electromagnetism, but only at incredibly tiny distances. It's what holds the nucleus together despite the electromagnetic screaming trying to tear it apart. This force is so strong that breaking it apart, nuclear fission, releases the energy of atomic bombs. But let's zoom out to the electrons again. Why don't they just crash into the nucleus? In classical physics, they should. An electron orbiting a nucleus is accelerating. Accelerating charges radiate energy. They should spiral inward and collapse into the nucleus in a fraction of a second. Every atom in the universe should implode instantly. Obviously, that doesn't happen. You exist. The universe exists. The reason is quantum. Heisenberg's uncertainty principle saves us. You cannot know both the exact position and exact momentum of an electron simultaneously, not because your instruments aren't good enough, because those two properties don't exist with precision at the same time. If you confine an electron to a tiny space, like forcing it into the nucleus, you've made its position very certain, which means its momentum becomes wildly uncertain. So uncertain that it would have enormous kinetic energy and immediately blast back out. The electron settles into the smallest orbit where this balance works out. It can't get closer without gaining so much energy that it escapes. The atom is stable not because of forces balancing like a solar system, but because of quantum uncertainty setting minimum boundaries. This is why atoms have specific sizes, why chemistry works, why you don't collapse into a point. And here's something even stranger. Quantum tunneling. An electron doesn't have enough energy to escape a certain barrier? Doesn't matter. There's a probability, small but real, that it just appears on the other side. It tunnels through, classically impossible. Like walking toward a wall and occasionally passing straight through it because you happen to be in the right quantum state. This isn't rare. It happens constantly. It's how the sun works. Hydrogen nuclei in the sun's core don't have enough energy to overcome their electromagnetic repulsion and fuse, but they tunnel through the barrier anyway. Every photon of sunlight exists because of quantum impossibility becoming reality trillions of times per second. You are alive because of quantum tunneling. Feynman understood something most people don't. The math isn't a description of reality. The math is reality. When the equation says an electron is in multiple places, it is. When it says particles can tunnel through barriers, they do. The universe doesn't owe you an intuitive explanation. And the deepest truth? These aren't exceptions. This is how everything actually works. Classical physics, the world of predictable orbits and definite positions, is the illusion. It's just what quantum mechanics looks like when you zoom out and average over billions of particles. Your solid table, your solid body, your solid world, they're all quantum foam pretending to be stable, appearing solid only because you're too big to see the underlying chaos. The atoms that make you aren't things. They're processes, probabilities, waves of potential collapsing into temporary existence every time anything interacts with anything else. So what does it all mean? Why is reality built this way? Feynman had an answer, and it's not the one you want. There is no why in the way you're thinking. The universe doesn't operate according to human comfort. It operates according to principles that simply are. But here's the revelation that changes everything. The strangeness isn't a bug. It's the only way reality could possibly work. Think about it. If electrons had definite positions and trajectories, atoms would collapse. If quantum tunneling didn't exist, stars wouldn't shine. If particles weren't waves, chemistry would be impossible. The bizarre quantum rules aren't arbitrary cosmic jokes. They're the precise requirements for a universe that can exist at all. The uncertainty principle isn't uncertainty. It's constraint. It's structure. It's the universe enforcing mathematical consistency. You can't have infinite precision in position and momentum because that would allow infinite information in finite space, which would create logical paradoxes and energy violations that would tear reality apart. Wave-particle duality isn't contradiction. It's completion. A particle is a collapsed wave. A wave is an uncollapsed particle. They're the same thing in different states of interaction. Your confusion comes from expecting reality to fit into linguistic categories invented by apes who evolved to throw rocks and avoid predators, not to comprehend quantum fields. And here's what Feynman knew that most people miss. The math isn't complicated because nature is hiding something from us. The math is complicated because we're trying to translate quantum reality into classical language. We're trying to describe four-dimensional geometry using only the words left, right, and sort of diagonal. The universe at its deepest level isn't made of things. It's made of relationships, of interactions. An electron doesn't exist in isolation. It exists as a set of probabilities that collapse when something measures it. But something measures it just means it interacts with another quantum system, which is also probabilities, collapsing into other probabilities. Its probability waves all the way down, collapsing into temporary certainty whenever they touch each other, creating the illusion of solid reality. You are not a collection of atoms. You are a pattern of quantum interactions maintaining temporary coherence. Every electron in your body was once in a different star. Every atom has been part of countless other structures. What makes you you isn't the particles, they're constantly being replaced. It's the pattern, the information, the relationship between quantum states. Consciousness itself might be a quantum process, not in the mystical sense, in the real sense. Your neurons maintain quantum coherence just long enough to process information in ways classical systems can't. Maybe. We don't know yet. And that's beautiful, because the same math that predicted antimatter, that predicted quantum computers, that predicted the Higgs boson decades before we found it, that math is still revealing new things. Feynman said, "If you think you understand quantum mechanics, you don't understand quantum mechanics." But he also said this, "I think I can safely say that nobody understands quantum mechanics." Do not keep saying to yourself, "But how can it be like that?" Because you will go down the drain into a blind alley from which nobody has yet escaped. Nobody knows how it can be like that. And yet here we are, in a universe that shouldn't make sense, where nothing ever touches, where particles are waves, where observation creates reality. A universe that works. A universe that allows complexity to arise from simple rules, that allows stars to shine, atoms to bond, life to evolve, minds to wonder why any of this exists. The mystery isn't a problem to be solved. It's the nature of reality itself. And maybe that's the final lesson Feynman wanted us to understand. The universe is under no obligation to make sense to you. But it's real, and it's beautiful, and it's stranger than you can imagine.